Hey guys, today I want to present the solution to the IMO Shortlist 2009 problem C1. At first, let's have a look on the problem statement. We have given 2009 cards, I label them 1, 2 up to 2009, lying in a row and showing a gold side. The other side is black. Now, two players play a game and they alternate moves. In a move, a player chooses a gold showing card K and then turns the cards K, K plus 1 and so on up to the card K plus 49 to the other side. Now we are asked two questions. The first is if the game necessarily ends. And the second question is if player 1 can force doing the last move. In the way the second question is asked, we may guess that the answer for the first question is yes. So the first thing we want to do is to try to prove that the game indeed will end at some point. To do this, we want to use a very common strategy which is really helpful to prove that a game terminates. And the strategy is to find a semi-invariant. We see that after turning the first card to the black side, it is no longer possible to turn it again back to the gold side. Moreover, if we have a look at our second card, then after turning the second card to the black side, it's only possible to turn it back to the gold side if we turn card 1 to the black side. But that is something we don't want to do. This motivates us to create a semi-invariant which puts a large weight to the cards on the left side. Therefore, the idea is to interpret the cards as a binary number A1, A2, and so on up to A2008, A2009. Here we want AI to be equal to 1 if and only if the card I shows black. We call this semi-invariant S of t, where S of t is the value of this binary number after our tth move. And now we are interested in the value of S of t plus 1 minus S of t. Since we are only turning the cards K, K plus 1 and so on up to K plus 49 to the other side, it is enough to have a look at these values of AI. And therefore we can write this as the sum going from I equals to K of t plus 1 up to K of t plus 1 plus 49 of AI of t plus 1 times 2 to the power of 2009 minus I minus the corresponding term for t. This can be written only in terms of AI of t because we know that AI of t plus 1 is equal to 1 minus AI of t. Therefore we get that this sum here is equal to the sum going from I equals K of t plus 1 up to K of t plus 1 plus 49 of 1 minus 2 times AI of t times 2 to the power of 2009 minus I. Since K is a gold showing card, we know that the value of AK of t is equal to 0. And therefore, even if all the other AIs are equal to 1, we can bound this sum here from below by 2 to the power of 2009 minus K of t plus 1 minus the sum going from I equals to K of t plus 1 up to K of t plus 1 plus 49 of 2 to the power of 2009 minus I. By the formula for the geometric series, we know that this is greater than or equal to 1, and therefore we know that our value S of t increases in every turn. Because this binary number here can only attain 2 to the power of 2009 different values, we know that after at most 2 to the power of 2009 moves, the game ends. Therefore, our answer to the question A is indeed yes, and we are done with the first part. Let's go on with the second part of this problem. Here, the main idea is that if we take some integer n less than or equal to 50 and have a look on the set n plus 50, n plus 100, and so on, then we know that in each turn exactly one of the cards in the set get turned onto the other side. Since in every move we turn the cards k up to k plus 49 to the other side, we know especially that k can be at most 2009 minus 49. Therefore, every card between 1 and 2009 minus 49 is choosable, and thus our idea is to choose this set in such a way that all of the cards in the set here are choosable. This directly implies that the number 1960, which is exactly 2009 minus 49, must be in this set. In order to fulfill this, we take n equals to 10, and then our set is the set 10, 60, and so on up to 1960. The absolute value of this set here is equal to 20, and this means that in the beginning the number of gold showing cards from the set is even. Together with the fact that in every move exactly one of the cards from the set here changes the color, we know that after an odd number of moves, an odd number of these cards here show the color gold. Hence, we know that before any move of the second player, there is at least one gold showing card here in the set. Therefore, the second player can choose this card and is therefore able to make a move. So, player B can always make a move, and since we already figured out that the game will end, we know that player 1 is not able to win this game,